Solving systems of two equations using linear combination, aka elimination. Elimination has the following steps. First, write the two equations with all variables on one side and like variables lined up vertically. Second, multiply the two equations by constants to change the coefficients of one of the variables into opposite values. Third, add down to eliminate the variable with opposite coefficients and obtain a new single variable equation. Fourth, solve for the value of the remaining variable. Fifth, substitute the value found in step 4 into one of the original equations and solve for the value of the eliminated variable. Now let's consider two examples. In this example, we note that the first equation, 2x equaling 3y plus 16, does not have all the variables on one side. So we must first move the 3y to the left. Subtracting 3y from both sides of the equation, we obtain a new equation, 2x minus 3y equaling 16. This is our first equation. We already have the second equation in the form we want. Lining up the variables, we obtain 2x minus 3y equaling 16 over x plus 3y equaling negative 1. The second step is to multiply a variable in each equation to obtain opposite values. In this case, we note that negative 3y in the first equation and 3y in the second equation are already opposites. Therefore, no work is required for the second step. We will now add down to eliminate the y, leaving us with 3x equaling 15. Dividing both sides by 3, we obtain that x is equal to 5. Now we'll substitute the value we've just found back into one of the original equations. In this case, we'll use the second equation, x plus 3y equaling negative 1. Subbing in 5 for x, subtracting 5 from both sides, we obtain 3y equals negative 6. And dividing both sides by 3, we obtain that y is equal to negative 2. Therefore, the solution to this system is the point 5, negative 2, and the two lines intersect at the point 5, negative 2. Let's consider a second example. In this case, both equations require the variables to be moved to the left. Starting with the first equation, 7x equaling negative 6y plus 3, we add 6y to both sides to obtain a new equation, 7x plus 6y equaling 3. Taking the second equation, we add 9x to both sides to obtain a new equation of 9x plus 4y equaling negative 11. Now we have our system of equations with our variables lined up vertically. We note that in this case, we would like to eliminate the y value. We will now therefore need a lowest common multiple for 6 and 4. This value in this case would be 12. Multiplying the top equation by 2 and the bottom equation by negative 3, we obtain two new equations, 14x plus 12y equaling 6, and negative 27x minus 12y equaling 33. Since the value of the coefficients in front of the y's are now opposites, we can add down to obtain negative 13x plus 0y equals 39, or really, negative 13x equals 39. Dividing both sides by negative 13, we obtain that x is equal to negative 3. Substituting back into the original equation 4y equaling negative 9x minus 11, we obtain that 4y equals 27 minus 11, 4y equals 16, and dividing by 4, we obtain that y is equal to 4. It's worth noting that we don't necessarily have to plug into one of the original equations. We can use one of the rearranged equations. In this case, what if we instead substituted into 7x plus 6y equaling 3? In this case, we obtain that 7 times negative 3 plus 6y equals 3, negative 21 plus 6y equals 3. Adding 21 to both sides, we obtain that 6y equals 24, and y is still equal to 4. Therefore, the solution to the system is the point negative 3, 4. Again, to review the steps, write the two equations with all variables on one side and like variables lined up vertically. Multiply the two equations by constants to change the coefficients of one of the variables into opposite values. Add down to eliminate the variable with opposite coefficients and obtain a new single variable equation. Solve for the value of the remaining variable. Substitute the value into one of the original equations and solve for the value of the limited variable.